So in this lecture, we're going to discuss the equatorial and axial positions found on cyclohexanes. So let's begin by looking at monosubstituted cyclohexane. So let's discuss methyl cyclohexane. Now recall that at room temperature, our cyclohexanes exist in two possible chair conformations. We have one chair conformation and the second type of chair conformations. Now when chair conformations interconvert from one to the other, axial positions become equatorial positions, and equatorial positions become axial positions. So, when this methyl cyclohexane with the methyl group found on the axial position interconverts to this chair conformation, the axial methyl group becomes equatorial methyl group. So the axial becomes equatorial and the equatorial becomes the axial. Now my question is, which one of these chair conformations is more stable? Which one is lower in energy? Well, to answer that question, let's draw out our Newman projections. So in this Newman projection, we have the following bump created. So there is a bump or steric hindrance between this methyl group and this chain and our ring structure. Now in this Newman projection, we no longer have that bump. We no longer have our steric hindrance between the methyl group and our ring structure, because the methyl group is oriented as far away from this ring structure as possible. In other words, in the axial distereomer, now these two molecules, these two compounds, and these two compounds are distereomers. That simply means they're stereoisomers that are not mirror images. So, in the axial distereomer, there is a destabilizing interaction between the methyl group, this methyl group, and our ring structure. On the other hand, in the equatorial compound, the methyl group is far away from the ring structure. So what's the result? What's the generalization that we can make about these two chair conformations? Well, larger side groups are more likely to be found on the equatorial position. In this position, there is less steric hindrance, and thus the distereomer is more stable. In other words, at room temperature, this molecule will predominate. This chair conformation will predominate. We're still going to see this chair conformation, but there will be more of this chair conformation because this equatorial position is stabilized by the fact that this methyl group, this side group, is as far away from the ring structure as possible. So now let's look at Dyesubstituted cyclohexane. So let's look at trans 1,2-dimethyl cyclohexane. So here we have one methyl group found on the axial position and the second methyl group also found on the axial position. Now once again, if we're at room temperature, this conformation, this chair conformation will interconvert to the following chair conformation. So these two axial methyl groups will now be found on the equatorial positions. So here we have both methyls are on the axial positions, and here both methyls are found on the equatorial position. So which one of these chair conformations is more stable? So once again, to answer the question, we have to draw our Newman projections. So let's begin with this Newman projection. So here we have the two methyl groups directly opposite of one another, and both of these methyl groups, these side groups, interact with our ring structure, and these bumps, the bumping between these methyl groups and the ring structure destabilizes the molecule. And let's look at what happens in this Newman projection. Now our two methyl groups are as far away from the ring structure as possible. Although we still have this single bumping interaction between our two methyl groups, we no longer have the two bumps we have here, and therefore this will be smaller in energy, more stable than this less stable, higher in energy chair conformation. So Trans 1,2-dimethylcyclohexane exists predominantly in the di-equatorial form, in which both of these methyl groups are on the equatorial position. And generally speaking, whenever we have any R groups, any large groups, those groups are more likely to be found together on the equatorial position than on the axial position. Because on the axial position, there is a bumping effect that's created by the bumping or steric interaction between our methyl groups or the R groups and the ring structure. And that does not exist in this more stable conformation.